So, in yesterday's lecture, we were discussing about various nuclear models, and we started with shell model. And initially, we assumed two different types of potentials, like infinite well potential and also harmonic oscillator potential. And after solving Schrodinger equation, we obtained the set of energy levels possible to be taken by nucleons. And we found that those energy level schemes were not able to explain the occurrence of energy gaps and also the magic numbers observed. So we just thought to change the potential to a realistic one where the potential assumed is not infinite but it's a finite one with a finite depth and with tapering edges because we know from scattering experiments that nuclei also don't have sharp boundaries. So, assuming a potential with tapering edges and with finite depth, which has a functional form like this, which is called the Woods-Saxon potential, Schrodinger equation was solved, and we tried to obtain the energy level scheme, but it was found that the energy scheme that was developed using Woods-Saxon potential also couldn't satisfactorily explain the occurrence of magic numbers. We know that magic numbers or shell closures happen to occur at 2, 8, 20, 28, 50, 82, and 126. These were assumed to be locations of shell closures from evidences which were obtained from various experiments. So it was assumed that these configuration or when nuclei have these many number of nucleons or when the occupation number of each level happens to be this, the nuclei are extra stable and properties change very drastically when numbers shift from these occupation numbers. So, at these occupation numbers, nuclei have some special properties, some extra stability, etc. So, uh, this potential also gives a set of energy levels which cannot explain all the magic numbers properly. Of course, the initial few magic numbers can be reproduced, but beyond that, the energy gaps as well as magic numbers seem to go wrong. So, we changed the potential from infinite to finite, but that also doesn't seem to be working. For the infinite potential well case, also, we saw that the magic numbers up to 20 was proper, but beyond that, the magic numbers cannot be properly reproduced. So, it is not only a factor of the depth of the potential well, but there has to be some modification in the basic assumption of potential. And here we resort to some help from atomic spectroscopy, where we had a similar problem in explaining the fine structure of spectra obtained from various atoms. In order to explain the fine structure of spectra, if you remember the case of atomic spectroscopy, uh, we we know that in the case of say atoms like say hydrogen, the simplest one, certain spectral lines which were assumed to be a single line were not actually single line but they were closely spaced doublets. I hope you remember that point. So to explain the fine structure of spectral lines, a concept called spin orbit interaction was proposed. Spin orbit interaction was proposed in atomic spectroscopy. In atomic spectroscopy, to explain fine structure of spectral lines. Fine structure of spectra. But there you know that once we assume something called a spin orbit interaction, we saw that energy levels were splitting into closely spaced levels, and there was some reordering of energy levels because energy levels shift from their initial term center upwards and downwards, and which level shifts upwards, which level shifts downwards, that all we could find out from this concept of spin orbit interaction. By just doing some a little bit of calculation, we could understand which level was going down from the term center, which was shifting upwards, etc. A similar concept we are trying to introduce here also. We assume that in addition to the main potential, there is a term called spin orbit potential, which is of the functional form like this. This one, this term. This potential is called spin orbit potential. This is something which we had already mentioned in the case of atomic spectroscopy, but similar concept we are bringing in here. So we are adding a term to the main potential called spin orbit potential, which is of the functional form like this. And this L and S, these are the same things as in atomic spectroscopy. L is the orbital angular momentum, and S is the spin angular momentum. Okay, so when you add such a term, okay, if you remember we know that L and S coupled to give your resultant J, and we have a relation for J as J will be the resultant of L and S. Now, what are the values that J can take? J can actually take values from L plus half, etc. to L minus half. Okay, these are the different values that J can take. And when L equal to 0, J can take only the value half. That's a special case. When L equal to 0, J can take only the value half. But for other L values, J can take values from L plus half to L minus half, where each value differs by 1. So when you are considering, if you remember the case of atomic spectra, where you considered one electron systems, when the system was one electron system, then S is equal to half. And when L took values like 1, 2, 3, etc., when L equal to 1, let's consider this case, J would take values half and 3 by 2, isn't it? Now, the case when L equal to 2, J can take values 3 by 2 and 5 by 2, etc. So, in the case of one electron system, we saw that each level splits into 2. So, the level corresponding to L equal to 1, that is a P state, that would split into P half and P3 by 2. Level corresponding to L equal to 2, the D state, it would split into D3 by 2 and D5 by 2, etc. So, every state would split into 2. If we are introducing such a similar concept here, now what we would like to know is where each level goes. I mean, in the case of atomic spectra, we found out in the initial unsplitted case, suppose the level position is this one, and on splitting, we want to know the shift in locations of each energy level from the term center. That we will be evaluating here also soon. So, in this case, we are taking the same equation as we did in the case of atomic spectroscopy. When J is the resultant of L plus S, your J square would be L square plus S square plus 2L dot S. And from here you get an expression for L dot S as half J square minus L square minus S square. Okay. Now, what is J square? J square is J into J plus 1 H cross square. L square is L into L plus 1 H cross square, and S square is S into S plus 1 H cross square. Now what we would like to do is, see here you see that for a particular L value, J can take a value L minus half and L plus half. These are the two values that can be taken. So I would like to know for J equal to L plus half, what would be my L dot S? Because L dot S tells me where my level goes from the term center. Okay, so I am going to evaluate L dot S. And what is L dot S in the case of L plus half? In the case of L plus half, it would be, instead of J, I am putting in L plus half. J plus 1 would be L plus 3 by 2 minus L into L plus 1 minus S is half. Okay, half into half plus 1, that would give me 3 by 4. This much H cross square. Okay, this is my L dot S. Now just opening the brackets and simplifying, what will I get? I will get half, okay, H cross square by 2, let it be there. Now, when I open this bracket, I get L square plus 3 by 4. And now those cross terms, 3 by 2L plus half L, that would give me 2L minus L square minus L minus 3 by 4. That's it. So here I have my L square cancelling, 3 by 4 and 3 by 4 cancelling. And I am left with what? I am left with L H cross square by 2. Okay, this is my L dot S for J equal to L plus half. Now I would like to know what is L dot S for J equal to L minus half. My L dot S would become half times J into J plus 1, right? So J is L minus half. Now L minus half plus 1 would give me L plus half minus L into L plus 1 minus 3 by 4, that much H cross square. And here I will have half into, this is A plus B into A minus B format. So this will be L square minus 1 by 4. That's it, because half L and minus half L will cancel. And then I have minus L square minus L minus 3 by 4, this much H cross square. L square and L square will go, and what do I have remaining? I have a minus L. I have a minus L. Then what do I have? Minus 1 by 4 minus 3 by 4. What will I get? Minus 1 by 4 minus 3 by 4. What will I get? I'll get a minus 1 H cross square. So this will be minus of L plus 1 H cross square by 2. Okay. Now can you just tell me what is the difference between, so I see that one term is negative whereas the other L dot S was positive, right? This is positive L H cross square by 2 and this L dot S is negative L plus 1 H cross square by 2. Now can you tell me which level goes down? My term is something like this, right? So when I have my L dot S negative, what will happen to the depth of the potential well? Will the depth increase or decrease? If the depth has to increase, then the sign of this term and the sign of this term has to be the same. But when L dot S is negative, what happens? The depth decreases. And when L dot S is positive, the depth increases. Okay, so which level goes down? Which level goes down? This level will go down. This level will be the deeper one, and the level L minus half will be the upper level. Okay, so your higher J value, okay, so this will happen. Now, I want you all to just check what would be the separation between the two states. I mean, suppose if you have your L equal to 1 and your J will take values, say, because your S equal to half, J will take values half and 3 by 2. And of that, now we just saw that P 3 by 2 will go down and P half will be shifting upwards. Now I want you all to evaluate this separation. How will I get this difference between the two energy levels? I know these individual differences, isn't it? So I just need to subtract these two things. I will get the entire separation. Can you tell me what is the entire separation? Someone please evaluate and tell me. One is LH cross square by 2 and the other is minus L plus 1 H cross square by 2. What would be this entire difference? Someone please evaluate and tell me. What do you get? You just add up these magnitudes of separations, isn't it? This has shifted downwards, but it has shifted by this much magnitude, and this has shifted in magnitude by this much. If you add up these magnitudes, you will get the separation between the two energy levels. And when you add up the magnitudes of separation, what do I get? When you add these magnitudes of separation, what will you get? Three by two. Uh, how did you get that 3 by 2? I have an LH cross square. Then I'll have an LH cross square again plus 2L plus 1 H cross square by 2. So this would be 2L H cross square plus 2L plus 1. isn't it? Isn't it? Did I go wrong somewhere? Oh, oh, 1 minute. Not like this. L h cross square plus, this was L plus 1 h cross square, right? So it will be like this, right? Isn't it? So it will be 2L. Okay, here I have an h cross square. It will be 2L plus 1 h cross square by 2, right? Won't it be so?
Yes, yes.
Okay. So this is the separation between the two splitted energy levels. This is true for, we have solved it for the general case. So you need to just plug in the different values of L. So you can see that the spacing between the energy levels increases with increasing L, right? It has a dependence on L. So for L equal to 1, you can evaluate the spacing. For L equal to 2, you can evaluate the spacing, and you can understand for yourself that the levels spacing actually increases with increasing L. Okay, so as you progress to higher L values, the levels shift more and more from the term center. Okay, so just because this is happening, you can even have levels shifting upwards and regrouping themselves with other set of energy levels, so that energy gaps at required locations can be obtained, and you can explain very easily the occurrence of magic numbers. That you can see on splitting how the energy levels look like and how the occurrence of magic numbers are explained, that you can see in this slide. See, this diagram I showed you yesterday. This was before considering the spin orbit interaction. We saw that magic numbers only up to 20 could be reproduced. Now, to the same potential, you are adding a term called spin orbit potential, and your energy level, the unshifted energy level locations have been given here, and on splitting, how they become, that also has been given here. So you just see S state, it doesn't split because it has only one J value possible, because L equal to 0 here, and for L equal to 0, J can take only one value, which is half. So your S levels, except S levels, every other level has split into 2. And we just saw before that higher J value level goes down and lower J value level shifts upwards. Okay, so this is your 1s state, which remains as 1s half. 1p state splits into 2, p3 by 2 and p half. D state again splits into 2, d5 by 2 and d3 by 2. See, this is what I told. The energy levels actually shift upwards and downwards, and sometimes reordering of energy levels happen. Here see, before splitting, 1d was lower and 2s was higher in energy than 1d, but here you see on splitting the energy levels have shifted upwards, so that here this d3 by 2 is higher in energy than 2s half state. So such a reordering of energy levels can take place, and in some cases the shifting is so high that the upper energy level actually groups with some other set of energy levels. You even have obtained a gap here, energy gap here. But that much of reordering can actually take place due to this spin orbit interaction. So, when you are considering such a concept, you have energy level splitting, shifting, and regrouping of energy levels. And now you see that energy gaps are occurring at certain positions. And let us see the filling of nucleons in each of these levels and how let us see how magic numbers are reproduced. See, 1 is half, it can accommodate 2 nucleons, and the cumulative number filled up to the first gap is 2. Now the second gap occurs after p half, and 3 by 2 can accommodate 4 nucleons, and half can accommodate 2. So together p3 by 2 and p half can accommodate 6. And by the occurrence of next energy gap, you would have filled 2 plus 6, which is 8 nucleons. Now I have a set of 3 energy levels after which I have a gap. Now filling in those 3 energy levels, 5 by 2 can accommodate 6, half can accommodate 2, and 3 by 2 can accommodate 4. So I get 14 nucleons. Um, I get 12 nucleons here, 6 plus 8 plus 4. So after I reach when I reach the third gap, I would have filled 2 plus 8 plus 12, which gives me, no, uh, yeah, oh, isn't it correct? 2 plus 6, 8, yeah, 8. And by the next level I would have filled 14, and by the next level I would have filled, okay, I would have filled 20 nucleons by then. You just consider, to 8 you add all these nucleons which you are filling in individual levels. So with 8 I am adding 12 nucleons and I am getting 20 nucleons. So I fill 20 nucleons by the time I reach the third gap. Now the next gap occurs after F7 by 2, and 7 by 2 can accommodate 8 nucleons. So after 20 again 8 nucleons I fill, I get 28 nucleons and I reach a new energy gap. Like that, if you look at the locations of various energy gaps will occur by the time you fill a cumulative number of 50, 82, 126, etc. So magic numbers can be successfully explained by considering a concept called spin orbit interaction. Okay, so when this energy level scheme you have to study. When you are writing shell model, you should write the initial considerations of potential and the failures of those potential to explain the energy level scheme and occurrence of magic numbers. Then you should consider the realistic potential, and that also fails to explain the magic numbers. Then you should introduce the concept of spin orbit interaction, and then you should explain how your energy level scheme evolves so that it is possible to explain the occurrence of energy gaps at right locations and also the occurrence of magic numbers. Now, if we consider uh, what are the merits of shell model, there are certain very important benefits that shell model has given us. One is it can successfully explain the spin parity assignments of ground state of various nuclei. Ground states of various nuclei. One thing I would like to remind you in this case, uh, we saw that the energy level spacing increased with increasing L. So you should draw the P levels little bit closer. D levels will be slightly more separated than P. Your F levels should be more separated than D levels. Your G levels should be even largely spaced, etc. So just don't think this as some set of lines. Don't think it like that. When you draw the energy level scheme, you should be very careful as to draw the separation also properly. P levels will be the most closely spaced. D will be slightly higher. F levels will be slightly more separated. G will be even more separated. So the separation has to increase with increasing L. That also should be taken care of while drawing this. Okay, that you should keep in mind. Then, this is one of the main advantages that has been quoted for shell model. So we will just see how various nuclei in the ground states, how their spin and parity has been explained. We know that nuclear state is represented by I pi. This we saw in the first unit, where I is the nuclear spin and pi is parity, which is evaluated as -1 raised to L. Okay. So if you look at the energy level schemes, let us consider some of the initial energy, few set of energy levels. So I have S half P3 by 2 P half D5 by 2 S half D3 by 2 etc. So let us draw that energy level scheme here. Now as of now I am drawing these as equally spaced. Just don't do this for your exams. So you have S half, then P3 by 2, P half, D5 by 2, S half, D3 by 2, F7 by 2, P3 by 2, F5 by 2. I hope this is correct. Yeah, F7 by 2, P3 by 2, F5 by 2. Yeah, till then that would be enough for our present purpose. Now, what we should understand is protons and neutrons are present in the nucleus. So, you get the same set of energy levels for protons as well as neutrons, but they are not identical particles. Protons and neutrons are not identical particles. So when you are filling a particular energy level, an energy level can accommodate, see, your S half, it will be possible to accommodate two protons, and the same set of energy levels are valid for the neutron also. So it can accommodate two neutrons also, because you get they are of the same mass, they are under, in the same potential. When you solve Schrodinger equation, you get the same set of energy levels. So I am not drawing an additional set of energy levels here. I am just bifurcating the same set of energy levels, and I am considering the filling of proton, and I am considering the filling of neutron. Don't confuse yourself. Don't think that Pauli exclusion principle is violated and all. Nothing is happening like that, because these are not identical particles. These are different. I cannot accommodate a third proton here, and I cannot accommodate a third neutron here. But the same set of energy levels being valid for a proton as well as a neutron, I am not drawing the set of energy levels twice, but I am just marking a bifurcation here, and I am showing the filling of proton and I am showing the filling of neutron. Okay. Now, what I would like to add here is, in a nucleus, there may be more than one number of nucleons in a particular energy level. So how do you find out the parity? That is what we need to know. Parity is evaluated as minus 1 raised to L. See, for a nucleon which is present in the S state, your L is equal to 0 and pi will be minus 1 raised to 0, which is 1. Okay. So if here I have two protons in L equal to 0 state, let there be A, B, C, etc. number of nucleons in a particular energy level, then the total parity is given as product of individual parities. Okay, how many nucleons are there in a state? You just check. Then for each you can find out parity using this expression minus 1 raised to L, and the total parity of that state will be a product of individual parities. Okay, that much we need to know. Now we will just understand how the energy level schemes, how the spin parity assignments are explained for various nuclei. Suppose you consider the case of even nuclei. I hope you remember what are even nuclei. The proton number and neutron number both are even. Now in such a scenario, you can consider the various set of energy levels. We needn't draw every energy level, but a few energy levels. And just see, lowest level is S half, then you have P3 by 2, P half, then D5 by 2, S half, etc. And in each state, you know how many nucleons can be accommodated. S half 2 protons, the same set of energy level, 2 neutrons. Then P3 by 2, you can have 4 protons filled here. Same set of energy levels, you can fill 4 neutrons. P half again, 2 protons, 2 neutrons, etc. Since Z and N are even, always they will exist in pairs. See, here I have 4 protons. 2 protons pair with each other. So I have 2 pairs of protons here. Again, here I have 4 neutrons. I have 2 neutron pairs. So in the case of even nuclei, in all the energy levels, they may not be completely filled. See, for D5 5 by 2, it can accommodate 6 protons. But suppose in my nucleus there are no 6 protons, but definitely there will be an even number. I may have only 2 protons, that's fine, but they will exist in pairs. Okay, so in the case of even nuclei, all the nucleons exist in the paired state. And if you remember what we had discussed before, pairing actually increases the stability. Pairing is a state where the resultant angular momentum is zero. So when the resultant angular momentum happens to be zero, the nuclear spin will take the value 0. Okay, so for even nuclei in their ground state, all nucleons exist in pairs, and when we say they exist in pairs, pairing means the total angular momentum is 0 because that is the state of maximum stability, and uh, thus the nuclear spin takes a value 0. And if you consider the parity, in whatever state the nucleons are in, see here I have 2 protons in the D state. Always we consider the that the properties of the nuclei are governed by the valence nucleons. That is why in this type of shell model we consider that the nucleons present in the valence shell, they decide the properties. So here I have 2 protons in the D state. D means L equal to 2. Parity will be minus 1 square. This is already positive. I have two nucleons here. So pi A, pi B would be positive times positive. So I'll get my parity as positive itself. Now even if my protons or nucleons are existing in the p state for which parity is negative for p state because L is odd. So for odd L states, my parity will be negative. But that is only for one nucleon, isn't it? I will always have an even number of nucleons in even nuclei. So the product of parities will definitely be positive because I will have even number of negative signs, and product of even number of negative signs will give me a positive parity. So for all even nuclei, the ground states of nuclei will be 0 plus. Okay. This was found to be in excellent agreement with what was observed from experiments. So this prediction or this sort of a model could explain the spin parity of ground states of even nuclei. Now let us consider the case of odd A nuclei. Okay. When we consider the case of odd A nuclei, either your Z is odd or your N is odd. Okay. So if we consider the same set of energy levels, and we consider a specific example, so your S half, P3 by 2, P half, then D5 by 2, S half, D3 by 2, and if you consider the case of say uh, which odd nuclei, okay, nitrogen 15. If you are considering this particular example, it means I have 7 protons and 8 neutrons. So if you start filling, S will contain 2 protons, 2 neutrons are also possible. P3 by 2 can accommodate 4 protons, 4 neutrons, and now I have already filled 6 protons and I have only one more proton to be filled which goes into P half. And I have 2 neutrons to be filled which goes into P half. So my neutrons are all existing in pairs. But there is a lone proton which doesn't have another proton to pair with. Okay, so this will decide the spin parity assignment of my nucleus. And I know when I am writing a state like P half, it means J has the value half, isn't it? So my I will have a value half because there is only one nucleon, and whatever value that nucleon has, the resultant will take that value only. So since my J is equal to half for that single particle and there is only one single particle there without any pair, whatever value that J will take, I will also take that particular value. So I will be half. Now what is the parity for a P state? What is the parity for a P state? Parity is minus 1 raised to L, and for P state L is equal to 1, so parity is negative. So how will I represent the ground state? I pi will be half minus. I hope this is clear. Now if you consider another example, sorry. The energy level scheme that I am drawing is not at all proper, but it is just for the sake of understanding. The spacings are not proper, but it is just fine to understand the filling of nucleons. Now you consider the case of oxygen 15. Here, what is the difference between the previous case and this case? There, neutrons were all paired and proton, there was a lone proton. Here, the case is just reversed. Here, all the protons are paired and the neutron is a lone neutron. So, you have two protons here, two neutrons here, four protons, four neutrons, and one neutron here. So you needn't consider the protons in this case, and this lone neutron will decide the state of this nucleus. Here again, the resultant will take a value half and parity will be negative because the lone neutron is in the p state, for which L equal to 1. Okay, so the ground state of this nucleus is also half minus. Now you consider another example. 61 nickel. It has 28 protons and 33 neutrons. So I have to consider a little bit more number of energy levels here. Let me draw those energy levels. This would be enough, I think. S half, P3 by 2, P half, D5 by 2, S half, D3 by 2, F7 by 2, P3 by 2, F5 by 2. Okay. And now let me consider the filling of protons and neutrons. I will see that here I have 2 protons, 2 neutrons, 4, 4, then 2 protons, 2 neutrons, then 6 protons, 6 neutrons. So what is the number now? 6 plus 2 becomes 8, 8 plus 6, 14. Then again 2 protons, 2 neutrons, 4 protons, 4 neutrons. And now let's just check the number. 8, 14, 16, 20. Now here, by the time it reaches here, it will be 28, right? So by F7 by 2, I have 28. Now, so 28 protons, proton number is over. Now I have 5 neutrons more to be filled. And P3 by 2 can accommodate 4. Sorry, I have mentioned proton here. It's not so. This is neutron. So protons are already filled and I have 5 neutrons to be accommodated, of which 4 goes to P3 by 2 and the lone neutron will be in F5 by 2. So according to this model, what should be the spin parity of this nucleus? Someone please tell me. As per the examples that we saw just now, what should be the spin parity of this nucleus? Someone please tell me. What would be the spin parity assignment of this nucleus? Here the lone neutron is in F5 by 2 what will be the spin parity? Someone? Someone please try. We saw many two examples just before. So just considering that example, what would be? Nobody to guess? Okay. Anyway, it will be, since the neutron is here, it is in the 5 by 2 state. The nuclear spin would be 5 by 2 and parity would be for the F state. Since L is odd, it will be minus. This is what we expect. But we are finding that the spin parity assignment for this nucleus is not 5 by 2 minus. We see that it is 3 by 2 minus. So here comes an exception to our shell model. I mean, there is a difference in the spin parity assignment predicted from the single particle shell model and what is observed. How this difference comes, that we will see in the next lecture. So, what we should understand is shell model is capable of explaining spin parity assignments for nuclei whose mass numbers are less than 60 or 50. But beyond that, it is not possible to. There are some deviations from predictions and what is observed. So, that we will see in the next class. Thank you.